All right, welcome back, everybody. Welcome back to MTED 110. Today we're going to do lecture 4B. Let's go ahead and get started. Let me pull up the slides right here. All right, so last time we left off talking about activity 4A, and the previous lecture was all about addition and subtraction algorithms, right? So today we're going to continue our exploration of algorithms, but we're going to talk about multiplication and division. I'm actually really excited because the multiplication algorithms are like my favorite, so we'll get to those first. Okay, so first thing I want to do is I want to start off with this, and this is going to be one of those thinking moments where I want you to just take a few minutes and ask yourself this. What multiplication problem is represented below? Go ahead and think about it. Hmm. Okay, and now go ahead and talk out loud about it. What do you think the answer is? What problem do you think is being represented here? Talk to yourself, talk to your neighbor, talk to anybody you can. Okay, so I'm sure a lot of you came up with a lot of different answers, but let's see what this problem actually is. What is being represented here? This is the problem 14 times 23. Yep, that's right. This is 14 times 23. There's a lot of interesting interpretations, but remember, multiplication will always be able to be represented as an area. So let's just look at the length of the sides of this thing here, right? So this is length 10, and this is 1, 1, 1, 1. So this all over here has a length of 14. And then this is length 10, 10, and then this is 1, 1, 1. So this is length 23. Ah, it's a bad looking two. There we go, 23. So this is a way that we can represent multiplication using base 10 blocks, which is really cool, right? You can do it with base 10 blocks. Base 10 blocks are amazing for all sorts of things. But this is 14 times 23, and this is actually going to lead us into a deeper exploration of the area model. So first of all, the area model is required by the Common Core state standards, so you'll definitely be doing it. It's incredibly versatile, and you'll see here in this lecture just how versatile it is. It's just really amazing, I think. And it's extremely useful way beyond the elementary classrooms. So this is definitely one of those models that you should have the horizon in mind when you're teaching it, right? And we're going to see in just a minute here that this will extend way beyond basic arithmetic and things like that. Um, so here's an example of it. The idea is that you can always represent multiplication as an area, and how you break apart that area to do your calculations is kind of up to you. So like, let's take 12 times 23 here. Uh, you can think about each one of these as representing the length of a rectangle. Each one of those factors is the length of one side of a rectangle. And however you want to decompose that length in a meaningful way is up to you. So down here, there are some examples. So here it's broken up into, let me get a different color, 10 and then 2 on this side over here. That's because this length is 12 on this side. And then 23 is left alone. And what you do here is you basically just do the multiplications, but you can do them for each little block you've got. So let's see. Maybe doing 12 times 23 is too hard. I know it's too hard for me, right? But you can break it up into something more easy. What is 23 times 10? 230, right? So that area is 230. The area of that little rectangle there is 230. And then what is 2 times 23? What's 2 times 23? That's 46, right? So the area of that little sliver there is 46. And then if you want to know what 12 times 23 is, you just add up all that area, and that'll be the answer. So in this case, our answer is going to be what? 276. There you go. So that's the answer, 276. But again, you don't have to decompose it in that way. You don't have to partition your rectangle in that way. You can partition it in any way you want, and that's the best part. So let's look at that one, or let's look at the next one, I mean. Okay, so this one, rather than decomposing the 12, this student just decomposed the 23 into something that was more palatable, right? 10, 10, 3. Add those all up, and you're going to get 23. So the length of that side is 23. Now we're going to compute the area of each one of these little blocks. So let's try it. What is 10, or what's 12 times 10? 120, right? That's an easy computation. What is 12 times 10 again? 120. And then what is 12 times 3? 12 times 3 up there, that's 36. So if you add those all together, you're going to get 120 plus 120 plus 36, which is 240, plus 36, which is 276 again. Pretty cool, huh? I think that's amazing. But see, or you can break it up any way you want. And one of the more natural ways you might say to do it is to break it up based on place value. And that's what this third example shows here. So up here, we've got the quantity 23. And then down here, we've got the quantity 12. So all we did was we divided up our rectangle based on the tens and the ones. And so now we can compute those 4 sub-rectangles. Let's do that right now. What is 10 times 20? 200. What is 2 times 20? 40. What is 10 times 3? That's 30. And then what is 2 times 3? That's 6. And so if we add all those up, we're going to get 200 plus 40 plus 30 plus 6, which is 200 plus 70 plus 6, which we know is definitely 276 again. So that's why this model is so amazing, but that's not all. We'll do a couple more examples here. I did a few right there, but let's do 12 times 17. All you have to do is this, just draw a rectangle. Okay, and now how do you want to decompose these lengths? This side is going to be length 12, this side is going to be length 17. Where do you want to draw the lines? Well, I can't do 12 times 17 too easily in my head. I'm going to divide it like this. I'm going to kind of take a clue, or take a cue, I should say, from the first example on the previous slide and break it up like that. And I'm just going to leave 17 as is. That means this is going to be, let's see, 17 times 10, that's 170, right? And then 17 times 2 is 34. And that is going to give me 204. There we go, that's the answer. Is that the answer? Don't believe it? You can check your work, that's totally fine. But the model is what led me to the answer once again. I didn't know the answer in advance, right? But let's see, maybe that's too difficult, right? Like I know this is actually tricky, right? What's 2 times 17? It's not as easy as it might seem. So maybe instead of breaking it up like that, we should have broken it up a little more. Oops, actually. Let's break it up a little more. 10, 7, 10, 2. Now let's try that. Maybe it'll be easier to compute. Okay, what is 10 times 10? That's right, it's going to be, what is that, 100. 10 times 10 is 100. All right, now what is 10 times 2? That's an easy one, 20. Trying to erase these things. Got to come up with a new method here. Don't erase that. What is 7 times 10? That's 70, right? 70. And then what is 7 times 2? That's 14. So we're going to get 14 right there. And then we can add it all up. Let's see what we get. 100 plus 70 plus 20 plus 14. Let's see. I see that this is going to be 190 plus 14, which is 204. Lovely. Got it, right? Pretty cool, I think. It doesn't stop there at 2-digit numbers. You can split it up with any type of number. See, this is the best part. It can always be represented as an area, no matter what number you're using. No matter what number you're using, you can do it. 237 times 59, let's do that. Let's see, I'm going to change the color here. Okay. And I'm going to split it up based on place value, because I think that's the most natural for me. So this length is going to be 237. And this length is going to be 59. So what I'm going to do is this. I'm going to split this up into 50 and 9. And then I'm going to split the top up into 230 and 7. 230 and 7. And I'm going to go ahead and erase these over here, because we know what those lengths are. And if we're not sure, we can add those all up, right? Add 230 and 7, you get 237. All right, so now let's try to do this together. What's 200 times 50? 200 times 50. I think that's 10,000, right? 10,000? 200 times 50, what do you think? I don't know. How do the zeros work? Am I just trying to add zeros? Well, let's make sense of it, right? Don't try to rely on the symbols and the zeros. Is it 1,000 or is it 10,000? I don't know. Let's try to play around with it. What's 5 times 200? That one's a lot easier, right? That's 1,000. Ah, okay. There we go. That's 1,000. And then what's 50? Well, 50 is 5 times 10. So all we got to do now is multiply that by 10, and that'll give us 10,000. So that is 50 times 200. Sweet. All right. What is 50 times 30? That one's going to be 1,500 or 1,500. What is 50 times 7? Hmm, 350, right? What is 9 times 200? 1,800. What's 9 times 30? That's 270. And what is 9 times 7? Oh, I always forget these ones. See, these are the multiplication facts that you're supposed to memorize in elementary school, and I never did. And they even said that on my report card. I remember my mom telling me that I got a note on my report card saying that I wasn't doing my multiplication tables fast enough. What am I going to do? Oh no. Let's see. 9 times 7? I don't know what it is, but I know 9 times 9 is 81. And then 9 times 8 would have to be 72. So 9 times 7 would have to be 63. There we go. See? So even if I didn't know that, I can use benchmarks and other knowledge and count backward. That's what I did. I started with a number that I knew, 9 times 9, and then I counted down by nines until I got to 7 times 9. All right. Well, now all we have to do is add all this stuff up. So let's do that. We're going to do 10,000 plus 1,500 plus 350 plus 1,800 plus 270 plus 63. Add all those up, and you can use whichever method you want, right? You could use the standard algorithm, the expanded algorithm. Let's see. I just added the ones, and then to that we're going to add, let's see, I'll do the standard algorithm. This is going to be a 1 and an 8. See, 8, 9, 10, 11, 12, 13, 18, 19 over here, and then 3, and then 1. There you go, 13,983. And there you go, that's the area model. Not too bad, right? What about this? What about 4.3 times 5.2? Does the area model work? Can we use the area model here? Yes. Yes, we can. We always can. Area. Multiplication can always be represented as an area. So let's do it here. Let's do it right here. We're going to do 4.3 times 5.2. And I'm going to split it up based on place value. It's a nice natural split, right? Here's 4, and here's 0.3. If I add 4 and 0.3, I get 4.3. So once again, all of that stuff that we talked about in chapter, I should say this way, all that stuff we talked about back in chapter 2, that's coming back in a really big way here. So if your students are struggling with the stuff from chapter 2, our numeration system, this is going to be really, really hard for them to understand. And think about how all the addition we did over here in the previous example, right? Actually, I can just, yeah, this stuff. Here we're appealing to our numeration system a lot. We're appealing to place value a lot. Same thing with this, all of that stuff. So you need all that stuff from chapter 2 now. Okay, all right, and then this side I'm going to say is 5 and 0.2. Let's try to calculate it. 5 times 4, that one, not too bad. I can do that. 20, I know that one. I know that one. What is 5 times 0.3? Uh-oh. Maybe we should try to do the standard algorithm, right? Maybe we should do something like this. But why? We don't even need to. Let's just think about what multiplication actually means. Remember, multiplication is repeated addition. So what this is saying is it's saying add zero point 0.3 5 times. Let's see if we can do that. 0.3, 0.6, 0.9, 1.2, 1.5. There you go. It's 1.5. Sweet. No need to use an algorithm. We just used multiplication, the definition of multiplication, right? We just counted. How about this? What about 4 times 0.2? 0.2. Well, that's the same idea. It's going to be 0.2 4 times. 0.2, 0.4, 0.6, 0.8. 0.8. Boom. Got it right there. Now let's do the interesting one. What about 0.2 times 0.3? How could we use that to our advantage? It's like saying 0.2 0.3 times. So it's like the number zero point 0.2, but not even a whole time. It's like less than one whole time. It's 0.3 of a time. So what is that going to be? Hmm. That's weird. Well, let's leverage what we know about our numeration system. If this instead, if this instead were just a 3, then the answer would be zero point 0.6, right? But that's going to be too big. If I did this, if I did 3 times 0.2, that's going to give me 0.6, but that number is way too big because I'm not multiplying by 3, I'm multiplying by zero point 0.3, which is much smaller than 3. In fact, it's 10 times smaller than 3. So this number is 10 times too big. And if it's 10 times too big, that means it needs to go down a step in the decimal representation, right? So this is going to be 0.06. You can show that mathematically too. So do you believe me? Did what I say make sense? Do you believe me? You're just going to walk home? No, you just say no. Don't say you believe it. Let's prove it, right? Check this out. I can prove to you that it's going to work and that my reasoning made sense. And you should demand this type of proof. I'm saying this, 0.3 times, actually I'm going to write it like this, 0.3 times 0.2 is the same as this. It's the same as 1/10 times 3 times 0.2. I can prove this in a different way too, thinking about how I want to show it. And then this is going to be 1/10 times 0.6, which is going to be 0.06. In other words, this is 0.6 tenths, right? And if you've got 0.6 tenths, then you're going to have you're going to have 6 hundredths. That's what it is, 6 hundredths. And we can talk about this calculation more, and I can show you a lot of equivalent calculations like that if that helps you see the arithmetic process going on in my head. I'd love to show you more of that. Once you see this type of stuff, it makes it a lot easier to play around with these numbers, and it gives you more freedom and flexibility. Okay, so let's finish this one off here. We still need to add all this up. So let's add it all up. 20 plus 1.5 plus 0.8 plus 0.06. Let's see. That's going to be, I'm going to add these two right here. 1.5 plus 0.8 is 2.3. So we're going to have 20 plus 2.3 plus 0.06. That's going to be 22.36. And that's our final answer. Not too bad, right? Not too bad at all. This might seem a little bit cumbersome, but remember, your students are not going to be able to do the type of multiplication that you're comfortable with because you've been doing it for your whole life, right? This is the first time these students are ever going to see this ever in their life. They've never seen it before. They've never talked about multiplication before. It's up to you to show them this so that you can lead them to these efficient algorithms. The other thing is, once you get the hang of this type of procedure, you're going to notice that there are a lot of shortcuts you can take. A lot of shortcuts, as long as you're comfortable with our numeration system. That's it. Okay, what about fractions? What about fractions? What do you think? I'll leave this one for you to try, but you can split it up in almost exactly the same way, and it'll work in almost exactly the same way. Try it out on your own. I think I actually say that. Actually, you do that in the activity, so we'll wait until there. But check this one out. That's a multiplication problem. That's a product. Can it be represented as an area? Yes, it can. Yes, it can. And we're going to see how to do it right here. So some of you might remember this from algebra, right? Wait, am I looking the right way? Should say this. Algebra, down the way, right? Algebra is way over there, down the way for your students, right? It's coming later down the way. Well, we want them to be able to compute things like this when they get to algebra. So what do? We teach them things like the area model. So check this out. And this will look very familiar to some of you, I'm sure. Up here, we're going to do x plus 1, and here we're going to do x plus 5. And then you just do all the multiplications the exact same way that we did over here. Same thing. Notice that up here, actually, let me go to I mentioned it back here, but notice that up here, I had said earlier that if you add all these up, you get 237, right? Exactly the same thing over here. If I add these up, I get x plus 1. So it's the exact same structure. It's exactly the same structure. It's just beautiful. Okay, so before I get too carried away, x times x, that's x squared. X times 1, that's 1x. X times 5, that's 5 x's, and then 5 times 1, that's 5. And if you add them all up, you're going to get x squared plus 6x plus 5, a trinomial, right? There you go, a trinomial. So we're setting our students up for the stuff down the line, all right? That's the idea. Okay, so here's an example. This is a question from the grade 4 Smarter Balanced exam. So we expect a fourth grader to be able to do this. And it says to drag the numbers into each section, each one of these sections right here, and then drag the product to complete the equation. So it's literally asking them to model, excuse me, to model multiplication using the area model. So let's see if we can do it. All right, so let's see. What is 30 times 6? 30 times 6, that's 180. So we would take this and drag it up there. That's what we would do if we were taking this exam on our own. Like, or right now, if we were that student in front, we would do that. Let's see, what is 20 times 2? That's 40. So we're going to drag that up here. That's 40. All right, now what is 6 times 2? That's 12. So we're going to take this and we're going to drag it up here. 12. All right, now we have the entire rectangle filled out and we just have to add everything up. Let's do that over here. Or we'll do that over here. Oops. 600 plus 180 plus 40 plus 12. Let's see, 8, 9, 10, 11, 12, 13, 6, 7, 8, 832. So then we would have to take this and drag it right there. So that's what we're expecting fourth graders to be able to do. All right, now you have an idea of where they're headed at the end of fourth grade. Okay, so now we're going to talk about the standard algorithm versus the expanded algorithm. And let me zoom in for a minute here on this standard algorithm first. So students who have taken me before will know that I am not a fan of the standard algorithm, and I'll explain why right here. Let's go ahead and do this one together. Okay, let's go ahead and compute 56 times 34. Now, the standard algorithm says to first multiply the 6 and the 4, and then we're going to write a 2 up here, and then we're going to write a 4 down there. Why is that? Well, I guess it's because we're making that 2 mark how many 10s we've got. Maybe that's it. Okay, so now what does the algorithm say to do next? Next, it says to do this cross multiplication, right? So then I guess I'm supposed to say, okay, 5 times 4, that's 20, right? And I guess I'm putting the 20 down there. I mean, I think I'm supposed to, right? Or wait, no, maybe I'm supposed to, wait, am I supposed to put the 20 up here and then a 0 there? And then I can just, oh yeah, and then I can just add the 2 down, right? And that goes that. Oh, but wait, what about this 2 up here? What about this 2 up here? I totally forgot about that 2. What do I do with that? I add it, right? I'm supposed to add it, not multiply? Why am I multiplying the 5 and the 4, but not the 2? That's all right. You know what? The book told me to do it that way. The book is always right. Everybody's always right, you know? So I'll just believe the book. There we go. You get where I'm coming from? Okay, so this will actually be 20. What did we say it was? Oh, it's 22. All right, now what do we do? So now I guess we're supposed to put a 0 here. Why are we putting a 0 there? Yeah, I guess that's what the book said to do, right? That's what the book said to do, so that's what we're going to do. Okay, so now we're going to do this. 3 times 6, that is 18, right? Oh, wait, what about this 2? What do I do with that 2? Oh, that's right, I'm supposed to throw it away and pretend it's not there anymore. Okay, I guess I cross it out or something. We do that. Okay, and then it's 18, and then what am I doing? Do I write, I guess I write the 1 up here? But wait, why don't I write the 1 over here? Isn't it supposed to be that? Isn't it supposed to be up here, 18, just like we did before? Remember we put the 1 over the next column, or the 2, just like over here, we put the 2 in the next column, and then, I mean, I think that's right. Teacher, help me. What's going on? What's going on? Yeah, it's really confusing, right? In this case, you're supposed to put the, where is it? The 1 up here, right? Oh, wait, we forgot. We forgot. What is that 2 doing? Wait, is that 2? Wait, I forgot to erase that 2. Oh, man. I'm doing so poorly with this. I can't do this anymore, right? I can't multiply. I don't know how to multiply. I just don't know how to do it. And there it is. That's all it takes. All it takes is that experience for a student to just be completely overwhelmed by their emotions and just give up. And that's where we as teachers have to intercept. We have to intercept and not let that emotion overwhelm them. Okay. Let's go back through and do this more with fewer mistakes. I'll say it like that. Let's do this again. Okay, so the standard algorithm says to do this. 6 times 4 is 24. And then you do 5 times 4, and then you add the 2, and you will get 224. Then you're supposed to go through and erase the previous work that you did, and then you put a 0 here. The truth is you don't have to put a 0 there, and actually some countries and honestly just some districts will not put a 0 there when they teach the standard multiplication algorithm. Okay, so then we do this multiplication, and it's an 18, and we write the 1 up there. Okay, we write the 1 up there. And that's because 18 is 110 and 8 ones, okay? And then we're supposed to multiply 5 and 3, which is 15, and then add the 1 to get 1680. 1904, so we did it correctly. All right, so that's the standard algorithm, and I hope that my fumbling of the first example is enough to illustrate that this is not an easy algorithm to teach. It's hard to explain why you do it in certain way or why you do certain things in this algorithm, and it's hard to explain why you put things in certain places. You can do it, and it is definitely explainable, but you can see that it takes a lot of extra cognitive thought, cognitive thinking to get to that point, right? All right, so now instead what I would like to offer up is the expanded algorithm. So let's do the expanded algorithm. And I'm going to do it over here. We're going to do 56 times 34, and then we'll scroll back. So we're still computing 56 times 34. And now what we're going to do is, instead of following this algorithm, we're just going to think about what these numbers are actually representing, or I should say what these numerals are actually representing. So first, we're going to multiply 6 and 4. We're going to get 24 when we do that. But instead of putting the 2 up there or carrying the 2 or anything like that, I'm just going to write 24 down here. Okay, we got 24 objects when I did that multiplication. Now I'm going to do this just like we did over here, but instead I'm going to recognize that this 5 is in the tens place. So I'm not multiplying 4 times 5, not at all. I'm multiplying 4 times 50. What's 4 times 50? It's 200. So it's going to be 200, just like that. All right, now the next thing we're going to do is we're going to go like this. We're going to do 3 times 6, but once again, we're going to think about place value. That's not 3 times 6, because this 3 is in the tens place. That's 30 times 6. Well, what's 30 times 6? 180. We saw that earlier, actually. 180. And then last but not least, we're going to do this multiplication. But again, it's not 3 times 5. That's 30 times 50. 30 times 50, which is 1500. 1500. We're just going to write all those numbers below. We don't even need to write them below. We could write them anywhere we want. I could write them, I could take this and I could just write it over here if I wanted, or I could write it over here if I wanted, or I could write it down here if I wanted. It doesn't need to be right there, but it's a nice place to put it, so I'm going to go ahead and put it that way. I'm going to turn it a bit too. Okay, and now we're just going to add all that up. 4, 10, 5, 6, 7, 8, 1. Oop, wait, 5, 6, 7, 8, 9. My bad. Miscounted. And there it is. 1904. Same result. And let me ask you, which method did you think was easier to follow? Think about it. Yeah, actually take this moment and just think about that and talk to, think and talk. Think first. Which one was easier? Which one was easier? Okay, now talk out loud with yourself, with your neighbor, with a ghost, with your group, hopefully, right? Just say something out loud about what you just observed, and it'll help your brain process the information. All right. All right, so let's move on. Anyway, over here is there we go. Yeah, over here is the explicit form of it right there. Or I should say not explicit, but the nicely typed out form. And it's the exact same thing that we just did a second ago. So nothing new there. Okay, I happen to really like the expanded algorithm in particular because of this stuff down here. It's better organized, it appeals to place value, it makes visual sense, and it agrees beautifully with other models. And this is my favorite part. This is my favorite part. So, let's see, do I do it? I think I have some space back here. Let's look at this 56 times 34 again. Let's do 56 times 34 again back here. And let's just use the area model. Let's use the area model for a change. Let's use the area model. And I'm going to do the same thing I did before. I'm just going to split it up by place value because it's a nice natural partition. So I'm going to say 56, 34. Let me move this out of the way a little bit, turn it a bit. There you go, 56 times 34. And let's do the computation. Remember, 30 times 50, that's 1,500. 30 times 6, that's 180. 4 times 50, that's 200. And then 4 times 6, that's 24. Let's add those up. Let's add them up like this. Let's see, 1,500 plus 180 plus 200 plus 24. Looking familiar? 4, 8, 9, 10, 9. Oops, that doesn't go there. 1904. Yeah, does that look familiar? Because that's the exact same structure that you get when you do the expanded multiplication algorithm. Check it out. There it is, the exact same structure with the expanded algorithm. And you can show it with the area model. How beautiful is that? How beautiful is that? I could even just put that stuff right here, 56 times 34. And it doesn't matter which order you do those multiplications in because multiplication is commutative. I'm sorry, addition is commutative. You can do all the multiplications separately and then add them up in whichever order you want. That's freedom, that's flexibility. You're not latched on, you're not attached to that algorithm. You're just thinking about breaking up the numbers, breaking up the numbers in meaningful ways and doing smaller calculations that are a lot easier to process mentally, right? There's another method that y'all probably heard of. I think I talk about it later. I'll talk about it right now really quick though. It's either in a couple slides or it's right now. It's called the FOIL method. Hold on, let me see how far. Oh, there we go. So I did give myself some space. There we go. There it is. Here's the comparison of those two models. Or I should say the expanded algorithm and the area model. Okay, 1 second. Okay, forgot to mention the FOIL method, but I'll mention it right here. So I think most of you have probably heard of the term FOIL. It stands for first, outer, inner, last. First, outer, inner, last. And that's why it's called FOIL. Now, what's funny is there are some professors who are very, very much, or just some teachers, I should say, who are very, very much against using this word FOIL. And I totally get it. The reason they don't like using the word FOIL is because the acronym does not expand correctly if you have more than two binomials being multiplied. And I'll explain in a minute here. But I happen to really like this word and this language because students immediately latch onto it. And as long as they're just working with binomials like this, it works totally fine. And in my experience, once students are mature enough and experienced enough with binomials, they don't need to think about the word FOIL and what the letters represent anymore because they have a better understanding of the distributive property. So let's go ahead and work that out. One way you can compute 56 times 34 is to write it as 50 plus 6 times 30 plus 4. And the FOIL method is called that because what you do is you multiply the first terms. I'll show you right here. You multiply these terms together and you get 1,500. Then you multiply, see, these are the first terms. Then you multiply the outer terms, and that's going to be 200. Then you multiply the inner terms, that's going to be 180. And then you multiply the last terms, L, F-O-I-L, FOIL, and you end up with 24. Okay, so the reason that I wanted to do this method also is because once again, the area model agrees with it. And the expanded algorithm agrees with the area model. And it also agrees with the FOIL method. And it agrees with everything. And it's so perfectly structured and it's all interrelated. You can see it, right? You can see it all right there. Look, 1,500 from 50 times 30. 1500 from 50 times 30. 1500 from 50 times 30. It's the same numbers over and over again in three different ways, modeled in three different ways. It's amazing. Okay, so I hope you enjoy that too. And if you want to do more examples, I'll be happy to do it. You'll have to do some more examples. And in fact, you're going to do some examples right now. So let me go ahead and throw this up really quick. Just take a few minutes and try to compute a couple of these. Actually, especially try to compute that one and see what you get. How do you do that one? Hmm. Hmm. All right, and now go ahead and talk out loud with yourself, with your group, with a ghost, with somebody, and tell them what you did and how you were doing it and what you were writing down. Even if you just got to say it out loud to yourself, you should. All right, let's see what's next. Ah, this is a fun one. This is another another thinking one. Okay, so I'll give you another few minutes here. But this is the lattice algorithm for multiplication, and I've got two questions for you here. My first question is, oh no, I guess I gave the answer here. This is This is modeling the product 27 times 34. So my question is, what's the result, and can you make sense of this algorithm? Go ahead and take a few minutes and think about it. Hmm. Hmm. Okay, now take some time and talk out loud about what you were just thinking about, or say out loud what you were doing when you were writing down those calculations. Try that. Okay, so let's work on this together. So I think the first thing you can recognize when you look at it is that up here you've got 27, and down here you've got 34, right? So let's just look at what's going on inside these little boxes. Notice that if I multiply 7 and 3, I get 21. And if I multiply 7 and 4, I get 28. So that's where those numbers are coming from. That's how those blocks are getting populated, right? And then let's look at the next column here. If we do 2 times 3, we get 6, right? We'll put a leading 0 just so that we can fill in that space. And then if we do 2 times 4, we get 8. There we go. So now we have all of those little triangles filled in. Now what we have to do is figure out how they're getting the answer. What do you think the answer is? It's 918. That's right. The answer is actually right here. Let's see how that works. It's kind of the same thing that we saw with the addition algorithm, right? With the lattice algorithm for addition. You're basically adding these shoots together. So let's do that right here. If you add this, you're going to get 8. If you add these, you're going to get 11. 8 plus 2 plus 1. But then you're going to have to carry that 1, and it'll go up here. So that's where you get the 1 from 11. And then this is the 10 from 11. All right, and then you add 6 plus 2 plus 1, and you get 918. So the answer is 918. Pretty cool. Funny enough, some students really, really love this algorithm. Some students have seen it before, some haven't. Some students, it just like, boom, clicks for them. It's really amazing. That's what it's all about. Give students all the algorithms, give them all the models, and just watch their eyes light up when one of them clicks. It's amazing. Okay, so that's it for multiplication algorithms. Those are the ones that we're going to be exploring in this course. There are many others. There's another one that I heard of that I don't have on here called like stick multiplication or something. Um, if you Google it, like stick multiplication, I think that's what it's called. It's like you lay out these sticks. For example, the number 23 you would represent as like these two lines right here, and then you would do 3 over here for the ones. And then if you wanted to do times 51 or something, then you would do like this 3, 4, 5, and then 1. And then what you do is you count all the intersections that you've got, and that'll tell you how many of each. Uh, it'll give you the place value. You add all those up, add up all those intersections, and that'll be It'll give you the place value. So you can Google that one and look it up if you want. There's a lot of different ways to multiply, a lot of interesting ones. So, okay, let's talk about division. So first off, division algorithms vary greatly from country to country, a lot from country to country, division in particular. The standard division algorithm in the US can also be expanded and made simpler, just like the multiplication algorithm that we saw a moment ago. The thing to remember is this: division is repeated subtraction. So division algorithms often rely on the repeated subtraction interpretation of division. And we actually saw this in a video from chapter 3, I believe, lecture 3B, where we saw some students using that subtraction algorithm. And we're going to do it here, but we're going to see just how robust that, or I should say representation. We're going to see just how robust that representation is. So let's do this first. Let's use this as a motivating example. Let's compute 4,356 divided by 6 using the standard algorithm. Okay, let's try this. So the standard algorithm says we're supposed to write it like this. Okay, so already I'm kind of confused because I'm doing 4,356 divided by 6, but I'm supposed to write 6 before I write 4,356. And even if I were to like move this 6 up here visually, that's not the division problem that I'm calculating. So even the structure is already a little bit awkward, right? Okay, so let's see if I can remember how to do this. Okay, the teacher told me that I need to find the biggest number that's smaller than 43 that's also a multiple of 6. Okay, what are the multiples of 6? Oh, 36. Okay, so 36. 6 times 6 is 36. So I'll write 6, 36. Okay, and then what is 43 minus 36? That's 7, 75. Okay, how many times does 6 go into 75? 60, 66. Oh, 11 times. It goes in 11 times. Wait, maybe I can get one more. 66, 72, I think. 72. I think I can do that. That's 7. 72. And then we're going to subtract. We get 3, bring down the 6. 6 times 6 is 36. Ah, there we go. So the answer is 676, right? 676. Is that the right answer? I don't know. I don't know. Is that right? I can't tell. I got to go to my calculator. I got to go to my calculator to check. I don't know. I don't know if it's right. I got to check. Wait, that's not right. My calculator says that it's 726. 726. 676. But I did what the teacher said. I did the multiples and I said it only goes in and then all that kind of stuff. Can you see where the error is? Think about it for a minute. See if you can notice the error. That's right. The error is actually right at the beginning. The error is right at the beginning, and it's with this right here. So I said 6 times 6 is 36, which is correct. But the problem is that 6 times 7 is bigger. 6 times 7 is 42. So I can fit another 6 into 43. I can fit one more than I thought I could. And because I didn't know that, the rest of the algorithm fell apart completely. And this is actually a pretty tame example. It can fall apart even worse. But yeah, it failed. And it's very hard to see why it failed. But it failed because what I really needed was I needed to pick not only a multiple of 6, but I needed to pick the biggest multiple of 6. And I had to pick the biggest multiple of 6 that fit inside of 43. So once again, it's like I'm completely ignoring the fact that I'm not dividing. I'm not even talking about 43. I'm talking about 4,356. But for some reason, I was supposed to just ignore the 56, right? Ignore the 56 over there and just focus on 43. Got really weird, right? So why does that work? Why did that fail? I don't know. That's just what the book said, right? Wrong. No, you should always ask why. Don't accept that. Always ask why. Demand answers, demand explanations, demand reasons. So the reason is that this algorithm completely fails unless you pick the largest number, the largest multiple that's smaller than the number you're looking at. So what we should have picked here is 7. And then we would have gotten 42. And then we would have brought down the 5. Okay? Again, ignoring the fact that that 5 is actually a 50 and that 1 is actually a 100 and all that stuff. And then we'll say, okay, it goes in there twice to get 12. And then it goes in there 6 times to get 36. There we go. So now it's actually right. So the thing with this algorithm is that it requires a lot of prerequisite knowledge to work. A lot of prerequisite knowledge to work. And a lot of students can't pick up on it, or if they do, they don't understand why it works and they get stuck right here, right? How often do you dread doing division because you have to break out this algorithm? Be honest. How often do you dread it, right? Well, hopefully I can get rid of that. So we're going to do this expanded algorithm, and we're going to go back and use this algorithm on this example. So I'm just going to keep the structure that we've got for now. And what we're trying to do is we're trying to divide 4,356 by 6. So in other words, we're asking how many times does 6 fit into 4,356? And here's the best part about the expanded algorithm. You can pick any multiple of 6 that you want, as long as it's smaller than 4,356. Pick any multiple of 6. And you should go for the low-hanging fruit. And by low-hanging fruit, I mean go for easy multiples of 6 that you know. One that I can think of right away is 6,000. 6,000. How about 6,000? Oh, that's too big. That's too big. 6,000 is too big. We need something smaller. What about 600? 600. Okay. All we're going to do is subtract 600 from this. 600. But I know I could get a lot more multiples of 6 out of there. Let's pick a bigger multiple. What's a bigger multiple that you see? What's a bigger multiple of 6? You know what? Maybe I don't know. Maybe I don't know what a bigger multiple of 6 is. That's the biggest one I've got. Okay, let's subtract 600. But already I've got some anxiety, right? Because I don't know how to do this. Okay, let's break it up into manageable pieces. 600 is 2 times 300. Let's subtract 300 twice. So instead of doing this, let's just do 300 twice. And we're going to get 4056. And then what do we get from that? That's another one of those funky ones. 4,056 minus 300. Ooh, what could I do? What could I do? Think about it. Think about it for a minute. All right, let's try this. Let's subtract let's subtract 100 away and see if that makes it easier. If I subtract 100 away, I should have 3,956. And then I can subtract 2 more hundreds, right? 3, 7, 5, 6. Whew, okay, that's a little better. Is that right? That's right, okay. So even if it takes your students that much time to get through that step, that's totally okay. It's totally okay. They're not doing anything wrong. Let them do it. All right, now that was just one. Oh, how many 6s was that? That was 100 6s. I should keep track of that over here. Okay. So I took out 100 6s. Now, what's another multiple of 6? Well, 2,400. That's another multiple of 6. But how many 6s is that? 400. Okay, now this division, this subtraction is not too bad. Let's go ahead and try this one here. Let's see, minus 2,400, we're going to have 1, 3, 5, 6. There we go. And now 1,200 is another multiple of 6. So 1,200. How many 6s is that? 200. That's 200 6s. Okay, and then we're going to end up with 156. 156. How many 6s can go into that? 120. 120 is a multiple of 6. So how many 6s is 120? That's 20. 20 6s. So then I'm going to subtract 120, and I'm going to be left with 36. And that's another 6 of them, another 6 6s to get 0. So over here, this is number of 6s. This is what I've been keeping track of, number of 6s. And now we can just add them all together. What do we get? 1, 2, 3, 4, 5, 6, 7, 726. And there's the answer. 726. All right, so this one, I took a little bit of extra time going through it to show how this part right here has a lot of flexibility. You just have to start subtracting by numbers that you're comfortable with. And if you remember the video that we saw in lecture 3B, one of the students there, she just kept subtracting 13s. That's what it was. She was computing 169 divided by 13, I think, or something like that. And she just kept subtracting 13 away. She was like minus 13, some result, minus 13, some result, minus 13, some result. That's totally fine. You can do that. And then what happens is you start to recognize that you don't have to just keep subtracting such small multiples. You can pick really large multiples and subtract away. So that's the idea. So let's try another one. I'm just going to make one up here. Hopefully I don't beach myself, but we'll find out. Okay, let's try to do, how about, we'll pick another number in the thousands, 4,284, and let's divide it by, how about, let's do 6 again, actually. That's not too bad. All right, so what is a big multiple of 6 that you know fits inside of 4,284? Let's think about it for a minute. Go ahead and take a minute. A big multiple of 6 that fits inside of 4,284. What do you think? I'm thinking of the number 4,200. How many 6s is that? That's right, that's 700 6s. So we're just going to write that over here. 4,200. In fact, I'm going to go ahead and erase that over here. 700. There's 700 6s there. Okay, and then when I subtract that, what do I get? I'm left with 84. Okay, how many 6s fit inside of 84? I don't know off the top of my head, man, to be honest. Hmm, 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 hmm. Let's just go for the low-hanging fruit. What's a multiple of 66 that's beneath 84? How about 66? That's 11. And then if we subtract those, what do we get? We get 18. How did I do that? I was thinking about distance between the numbers. I'll go off to the side and show you. I was thinking 66 and 84 over here. And I was like, what's that distance? And actually what I thought of is I was like, okay, I need 4 to get up to 70, and then 10 to get up to 80, and then 4 to get up to 84. That's 18. There we go. So that's got to be 18. Now, how many 6s fit inside of 18? 3. Wow, I got lucky. 0. I actually picked a number that's divisible by 6. How nice is that? So this is going to give us 714. Sorry, 714. There we go. And that's the expanded algorithm. So the answer is 714 in the end. And again, notice that it doesn't really matter where I write anything or any of that stuff. It's all about using the numbers, not the numerals. Okay, so you're going to get a lot of practice with this on the activity and then also in your homework. And I just want to stress, do not use calculators. Do not use calculators in these sections. That defeats the whole purpose of these sections. These sections are specifically, and these chapters are specifically so that you can practice not using a calculator. So don't cheat yourself out of that. All right, here are just some examples of the expanded algorithm being used and being written in different ways. That's really all it is. So we saw stuff that was similar to all of these. Let's zoom in over here. There we go. Okay, so here, this student is just keeping track of how many 6s fit inside of that number. So they just picked, they basically picked a nice multiple of 6. They picked 3,000, right? And they said, oh, that's 500 6s. And that's what they're writing in this column. This column is number of 6s. Number of 6s. And then you can keep subtracting. They were like, okay, I subtracted 3,000. Now I've got that. What's a multiple of 6 that's smaller than 1,356? 1,200 is. 1,200 is 200 6s. And they keep repeatedly subtracting, on and on and on. And then the final answer, they didn't even list the final answer. The final answer is what you get when you add these up. So you're going to get, what is that, 726. There it is. All right, that's the idea. Okay. Now, the rest of these are similar. The one on the far right is an interesting one. There we go. So This is the same thing. This is still using the expanded algorithm, but this is sometimes called the scaffolding algorithm because the student is writing the results or the number of sixes vertically. So how many sixes is 600? It's 100 sixes. How many sixes is 120? It's 20 sixes. And then how many sixes is 6? It's 1 6. So the answer is 121 sixes. Or in other words, if I repeatedly added 100 or if I repeatedly added 6 121 times, I would get 726. Pretty cool. All right, so like I said, you'll get some practice with that. I can do more in the collaboration meetings. You just got to ask. I would love to do it. Let's talk about one last thing before we call it a day. And my question is this: why move the decimal point? So I want you to just ponder this and think about it with your group for a minute here. Why would you move the decimal point to make this problem easier? You know what I mean? Remember back in the day where your teacher would be like, oh, don't try to compute that. Just move the decimal point some number of spaces and then compute that. So why move the decimal point? Why were you told to do that? Hmm. Okay, so talk and see why do you think you were told to do that? Why does that help? Why does that help? Okay, so let's talk about this. One of the reasons that teachers tell students to do this is because it makes it easier. But why does it make it easier? Oh, sorry, I got to go back to this. Why does it make it easier? Well, it's because students are comfortable with whole numbers, but they're not comfortable with decimal or numbers that have a decimal smaller than one. But they shouldn't be. That's the whole thing. They shouldn't be because these are just numbers, and we're talking about division, which occurs on numbers, not numerals. So the fact that a student sees this and gets an anxiety or feels anxiety or gets scared, that's the problem that we're trying to address because they really shouldn't. They should be able to see these things as quantities. They should be able to see these things as quantities, not just symbols that they need to manipulate in just the right way to get the division to work out the way that the algorithm says it's supposed to. That's not what it's about. So what I encourage you to do is when you look at this, think about the quantities that are being played around with. So here, this is 56.98. Just take a moment and visualize where that number is on a number line. Try to visualize it as base 10 blocks. Try to visualize it as a size. Okay? It's about 57, right? So try to imagine the number 57 in your head. And now look at this number over here, 3.7. Again, just close your eyes and ponder the number 3.7. Think about how big it is. Try to see where it is on the number line, okay? And now think about what you're doing. You're trying to divide. So you're asking yourself the classic question, how many times does 3.7 go into 56.98? That's the question. And now maybe that you've taken the time to think about the size of those numbers, you can see it in a more intuitive way. We're just trying to figure out how many times 3.7 fits inside of 56.98. And we could even count partially, right? We could get a pretty good estimate, which we're going to talk about in the next chapter. We could get a pretty good estimate if we rounded things, right? So like it's basically like how many times does 4 go into 57? Hmm. Well, let's see. 4, there's 40, that's 10 times. 48 is 12 times. It goes in there a lot of times, right? Hmm. Well, we could figure it out if we just continued that way. So teaching students to do this and encouraging them to do that is actually, it's kind of, it defeats the purpose. We don't want them to do that. We want them to do this right here. We want them to think about those numbers as numbers. All right. And I'll show you an example why. So this division problem might not be too hard, but many students would be afraid to do either of these two. So what I want you to try is at home with your group, try to do these using any algorithm you want and just ask yourself what patterns you see. So take some time for a moment. Okay, now that you've thought about it and hopefully computed it, Talk out loud about what you computed. Talk out loud about what patterns you saw. What did you see there? What did you see happen? Okay, now let's talk about it here. 56 divided by 7, that's actually one of those multiplication facts that you're supposed to know, right? 7 times what is 56? Of course, I can't remember it, right? Okay, 7 times 7 is 49. So that means 7 times 8 is 56. So I know this is actually 8. Ah, okay. Now, 56 divided by zero point 0.7, I'm sure a lot of you look at that and you were like, okay, calculator or this type of thing, or I do the division algorithm. But again, I discourage you from doing that. I discourage you from doing that. Think about the size of these things, right? Let's think about how these questions are related. This is how many times 7 goes into 56, right? It goes in there 8 times. This is how many times zero point 0.7 goes into 56. In other words, how many times 7/10 goes into 56? Well, zero point 0.7 is quite a bit smaller than 7 itself. In fact, it's 10 times smaller, right? 7 versus 7/10, 7 versus 7/10, right? So that means that if I could fit 8 of those inside of 56, I can fit 10 times as many of those inside of 56. So that means I can fit 80. What's 8 times 10? That's 80, right? So this is 80. The answer is 80. I didn't need to use any algorithm at all. I was just thinking about numeracy and the size of these. Now let's carry that down to the last problem here. Okay, well, now we're not dealing with 56 anymore. We're dealing with 5.6. Well, compare 56 to 5.6 and you'll realize that 5.6 is 10 times smaller. So I'm going to be able to fit in 10 times fewer as many of these guys in there. So the answer is 8 once again. But the thing, oh, sorry, that's supposed to be an equal sign, 8 once again. But the thing I also like about this last problem is that you can do it just by counting. If you're comfortable with the numbers, right? Let's do this by counting. Here we're going to say, how many times does 0.7 go into 5.6? Let's count. 0.7, 1.4, 2.1, 2.8, 3.5, 4.2, 4.9, 5.6. It's 8. There you go. And you might have noticed those numbers as I was counting up, right? 14, 21, 28, 35. Do those numbers sound familiar? Those are the multiples of 7, right? Those are the multiples of 7. And it's the same thing here, except now we're doing the multiples of 0.7. So everything's been scaled down a little bit. Okay. Anyway, so I hope this is edifying and that it makes a little more sense now for why we want students to be able to do this, all right? Okay, so now let's play. Let's do activity 4B, or let's explain activity 4B, and then we'll call it a day. 4B, where are you? Okay, so here's activity 4B. It's basically just using these models that we talked about. So use the area model of multiplication to compute this. Hopefully you've practiced that a few times already. Area model of multiplication, area model of multiplication. Like I was saying, you'll get to do that on the activity, right? Oh, sorry, area model multiplication. Down here, I want you to specifically use the expanded multiplication algorithm. So one of the things that's on the module assessments are these algorithms. You need to be able to do each one. And then using the expanded algorithm of division to compute these, all right? And that's it. That's it for this activity. So just practicing with those algorithms, and I think that's just about it. Okay, then on that note, I'm going to go ahead and call it a day, and I will see you all for the next lecture, which is 5A. All right, have a good one.